Okay, let's go ahead and get started. First of all, I just want to make sure, just to pre-apologize for any coughing or clearing of throat that I do. Got a little cold or something going on, so I just want to mention that. So it's not too off-putting, hopefully, as we go through this. But welcome, everyone. We're going to be talking about the electronics cooling module that's a part of the SOLIDWORKS Flow simulation. My name is Andrew Smith, and I'm a simulation specialist. I specialize in CFD in particular, and obviously SOLIDWORKS Flow is a big part of that. So today we're going to kind of talk about this flow simulation component, this attribute, or this module that can be added on to flow simulation. Those of you that maybe have a up-to-date SOLIDWORKS license that may have seen this if you use Flow. As of 2023, you have access to this ability to manage which one of your Flow licenses you're using. So in my case, I have access to the Flow simulation as well as the HVAC and electronic cooling module. As of 2023, you can actually select which one you want to use. So in this case, we're going to be using this flow simulation with the electronic cooling module on top of it. But I just want to cover a couple of the differences we see here. So I have here my simulation tree with all my things added in, all my possible items. And then I have here, I have the same tree just with the electronic cooling module added on. So you can see it adds a few capabilities, including these things. We'll go through each of these in turn. Yeah, so again, the left side is the regular SOLIDWORKS Flow without any additional modules, and the right-hand side is showing us the additional capabilities we have with the electronic cooling module. We'll get into more of that as we go. Again, just to reiterate, SOLIDWORKS Flow works as an add-in to SOLIDWORKS. We can add on additional capabilities by adding on the electronic cooling module or the HVAC module. We're going to be focusing on electronic cooling module today, like I said, and just to be just show sort of what we have here. These are the tools that are available with SOLIDWORKS Flow. You can see we have like all the check marks on the left-hand side, and in the middle column we have the HVAC. You can see most of them that are checked are also checked on the SOLIDWORKS Flow side. Same with electronic cooling. There's only a couple differences. I've circled down there at the bottom the electronic conditions sort of thing, and that's basically what we're going to get into. And that if you look at this electronic cooling, click that plus button, it expands into this list. So this is kind of our starting point for today, where we're looking at just what these different tools do. So we'll kind of work through these one by one. We'll start with the heat pipe and just kind of briefly talk about what it does and how it's helpful in progressing this simulation tool. All right, so heat pipes. This is what heat pipes typically look like inside an electronics enclosure. Usually they're copper. They are fully enclosed, and they're pretty incredible little devices. The way they work is they have a porous sort of substance that lines the inside of this copper. Usually it's a copper tube. Inside that is also some sort of liquid. This liquid, when it's heated, will produce vapor that'll move to the cool end of the heat pipe. And as it gets closer to the cool end, it cools and condenses back down into the porous media, and then that is transported over back to the hot side as a liquid, and then it again re-evaporates, and that cycle continues. They're really very capable tools. Heat pipes transfer that heat from a hot surface to a cool surface, and they can have heat fluxes anywhere from 10 watts per centimeter squared to up to 20 kilowatts per centimeter squared. So it's really very efficient in the right conditions. So used a lot of times in high power electronics. We can now, those of you that are familiar with CFD may know that this is a computationally very expensive process to capture the evaporation, the condensation, and the transport as in a porous media. It's all very expensive. And so SolidWorks has made the heat pipe basically a simplification tool. The way this works is you create a solid body. I'll show you an example of that momentarily. And then you simply select which part of that solid body is the hot side. And then you select a cold side, so the heat in face, the heat out face, and then you say it's effective thermal resistance. This is what it tends to look like. And doing that simplifies that really complex body, that really complex process down to just a simple solid, and then SolidWorks uses empirical and theoretical formulae to calculate the heat transferred through this body. So saves a ton of time versus trying to capture that data. And as you probably know, SolidWorks Flow is can't capture that phase change even. So this would be something you can't do unless you have access to these heat pipe tools. The next thing we're going to talk about is thermal joints. Thermal joints in the lingo here in the jargon of SolidWorks is not what you may have thought of as a thermal joint in the past. Thermal joints, maybe you're imagining something that's bendy and that can handle the fact that it expands and contracts as you get hot. As far as we're concerned in this module, a thermal joint is really just the ability to transmit heat between two faces. So I don't have any fun pictures here, but we have the ability to add a thermal resistance between two parts that are touching. If we want to expand past that and be able to say, hey, I want to transmit heat from one surface to another, I can just use this thermal joint tool, and that'll save me a bunch of time instead of having to go and model parts. And maybe these parts are complex and computationally expensive to mesh. I can just say, hey, I know there's a certain amount of heat transfer happening between these two faces. So you choose the two faces that are going to be exchanging heat. You can either put in a heat transfer coefficient or the thermal resistance between the two faces, and the computer will solve the rest for you. So that's a really handy tool to be able to get thermal joint behavior figured out quicker. So, all right, so thermal joints we got done. We're going to talk about two resistor components. Two resistor components are essentially simplifications on a chip. So there are other models for how to simplify the heat produced by excuse me, chips, but this is one that's kind of the industry standard. It's really simple and really easy to use. And as you can see, you basically have your chip here in this zone. You have the case, which is shown in red, or the package. Excuse me, the package is shown in red, and the case is shown in blue, and that all sits on the PCB shown in green. The idea is that the chip's producing heat, and one of the best ways to sort of simplify this is to say the heat's being produced, or a current's being produced, and as it passes through these resistors, that heat is passed along to the PCB, and not all of it does, because there's some resistance. Some of that's going to be pushed out just directly into the air. We'll talk about that momentarily as well, how that all works. The process for setting up a two resistor component is the same as we've seen. We select the top face in this case. When we do that, the two resistor component is automatically applied. So if we choose the face that we want to have as our hot face, it'll select that body as our component. And then we have a huge library of chips available that come with the electronics cooling module. If you're using just SolidWorks standard, if you're using just SolidWorks Flow without the electronics cooling module, you may have access to some two resistor components, but it's a small list. And as we'll point out momentarily, when you have the electronics cooling module, your library of available tools is much larger. If a chip that you want or a component you want to have in your circuitry is not there, we can actually create our own model. And then as you can see here, we just select the heat output of the chip. If you are wanting to create your own, you can take an existing two resistor component and modify it so that it looks exactly like whatever you're using. The library is quite large of available ones, and it's from a lot of the suppliers of these circuits as well. So there's a good chance that what you need is already here. This is what the typical behavior of these chips. This is how they're defined. You have the name obviously here. In this case, we have CBGAFC 10 by 10. You can add some comments here, and then we have just the junction resistance, resistivity between the case and the board here. And the idea is we can see that the resistivity from the junction to the case is pretty small, which allows heat to transfer through it pretty easily, but versus the junction of the board might be a little higher. It might be high enough that the heat is dissipated more to the air than into the PCB, and may indicate that we might want to put a heat sink on there. Anyways, we can modify these, like I said, so you can make your own specific chips if you have ones that don't match any of the ones available on this list. All right, we'll now talk about PCBs, or printed circuit boards. Typically, these are complex parts. They have multiple layers with multiple, as you can see, we got holes that are carrying copper through it. We got tracks of copper. We have internal tracks, upper tracks. There's lots of complexity here, and the thermal behavior of these PCBs can be difficult. We could probably model this all in SolidWorks as it is, but again, being able to mesh that would be computationally intensive, and then the processing time would also increase dramatically because we're looking at not only trying to capture the whole thermal behavior, but also we have to capture the way the heat transfers between these copper sections and the rest of the board. So it can be a little complicated. Fortunately, again, SolidWorks with the electronic cooling module has the printed circuit board basically shortcut. So we select the part that's going to be representing our PCB, and we can choose from a large library or create a new one. The way these look in the engineering database, they're like this. This is the one that comes as an example. The the library contains only one item here, so I think I said large library earlier, but it's actually just one item that you can modify that's used as an example. So in this case, this one is the 2S2P, so we have 2 signal, 2 power layers, and the conductor is the copper. And we can basically select how much each layer has, how conductive each layer is, and all that behavior in the definition section of the PCB. So it's a really powerful, easy shortcut that can really save us a lot of time when we're doing these electronics measurements. All right, and then I'm going to mention thermoelectric coolers. You may have noticed, if you're paying really close attention, that both the trees that I showed at the beginning both had thermoelectric coolers on them. You are able to make thermoelectric coolers from scratch if you want without the electronic cooling module. Once you activate the electronic cooling module, you have access to a much larger library of TECs. Yeah, we'll talk more about that in a minute, but basically they work similar to all these. When you insert the tool, you select the component, you select which face is the hot face, you select how much current is passing through it, and then select the model. Now this again is a large library, and you're able to choose the actual TEC based on your manufacturer. So I think we have both Marlowe and Melcor that are available here, and if you're using a TEC that's from somebody else, that's fine, and it's easy to create your own. And this is what they tend to look like. This again it's a large library, and if you need to make your own, you just simply name it and then add the values into your maximum pump heat, maximum temperature drop, maximum current strength, maximum voltage. So it all works out. So those are the sort of covering the list of things we have. Another thing that's included that's not shown on the SolidWorks website is what we call Joule Heating. Joule Heating is this process where you have a current, and that can be, we say amperage. We can create either a voltage drop or an amperage current that's flowing through a certain body, and we can actually produce heat that way. So if we do this without the electronic cooling module, we actually just have to put in a heat source and just say, oh, I can do some hand math and hand calculations and find out what the actual output of this is. But it may be better if I could have the computer do that complex math for me and find out how this all changes as I go. So here's just a simple example of a fuse that has a current running through it, and you can see when the current's low, and this is a temperature plot. Here you can see when the temperature is low, the current flows through and the temperature doesn't go very high. When that current increases, it goes up into the melting temperatures of this material and then causes the fuse to trip, therefore thereby deactivating the circuit. So we can do this for simple things like the fuse. We can do this for more complex assemblies. A couple things that make this really nice are we have access to the electrical source tool now with the electronic cooling module, so we're able to put in a current or a voltage and see how that passes through. And then we can also specify for a given face the contact resistance, or we can make it a perfect electrical insulator. So these are both things we have access to that we don't have access to without the electronic cooling module. If we do have current or voltage flowing through a part, we need to ensure that the resistivity value is here. Now with the electronic cooling module, we have a ton of parts, a ton of materials that have resistivity already plugged in, and that's really nice. The last kind of feature I want to talk about real quick is the expanded and extended engineering database. So this, along with everything we've talked about, so increased capability, SOLIDWORKS Flow with the electronic cooling module comes with expanded solid materials. So that's, again, we're looking at other alloys or other metals, other insulators and semiconductors, and all their behavior with thermal and electronics variables. We also have thermal interface materials. We have access to some we haven't touched on, fans. So we have more axial, more radial, more fan curves in general. A library of thermoelectric coolers, library of two-resistor components, and important thing to note here is that these libraries were developed in cooperation with suppliers. So you can see we have Delta, Comair, all these other businesses. These are just some of the manufacturers that have supplied the data to SOLIDWORKS so that we have access to the material properties. So we don't have to make our own each time. We have access to them ready to go. Now, that's super handy. And I really quickly, if I can, want to show just a couple quick example of how this works and what it all means. So I have just a simple part here where I have current. I have created a DC voltage, so I have about 1/10 of a volt that passes from this side, and then it's grounded on the other side. I have a copper and steel part, so this part's copper and this part's steel. And I just want to see what happens to the temperatures as I pass this current through here. And I'm not going to run it because it takes a little bit of time, but I'll just create this plot first. Get out of here. One moment. There we go. All right. So there we go. All right. So we can see that the current tends to pass through. Oops. There we go. It tends to pass through. We have this last sort of lighter blue going through the copper section. That should make sense as copper is a better conductor than steel. We'd expect more of the current to pass through when it has basically equal choice. And you can also see that as this steel piece narrows, we are able to we show that more current is actually passing through that as well. So just kind of a quick example. And then I also wanted to bring up this engineering database really quickly to show you just some of the expanded options we have. You may be familiar with this if you've looked at it before with fans. Typically, I have access, if I don't have the electronic cooling module, I have one fan. With the electronic cooling module, I don't have just one fan. I also have a list of brands. I have Comair, Delta, EBM, all these. And I can say, oh, I know exactly what blower I have. So if I have an axial fan, I can say, oh, I know exactly what I have. And I can look at the properties here. And also important to notice that these come with fan curves. So a lot of these will come with fan curves, and then we can derate these fan curves. So if I know I'm running this at 50% or 80%, I can run the fan like that in my simulations as well. Another thing I want to point out is materials. Typically with materials, I don't have access to a lot of this data, and then furthermore, I don't have access to, number one, the number of items on this list, and then number two, some of the characteristics here. So stuff like resistivity or electroconductivity, we don't have these options unless we have the electronic cooling module added in. Let's see if there's anything else I want to touch on. Oh yeah, again, thermoelectric coolers. We go from having none to having, again, large libraries of TECs we can use. The same with two-resistor components. Lots of options here. Okay, it's just going to be a short and sweet example here. If there's any questions, feel free to plop them into the questions section, and we'll get to them. Otherwise, yeah, it was great having you. Hopefully that was helpful, and you have some understanding of what the electronic cooling module includes and how it can help you in future studies. So, yeah, like I said, please pop any questions in the question section. But if not, thanks for coming, and we'll see you again soon.